And we're back. That video took a long time to upload. Not that, you're watching them in succession, so you don't know. But I just sat here in my apartment for far too long staring at my computer screen. Um, yeah, and if you're curious, this is where I live. I feel like these videos should start getting more interesting. Maybe a little, like, tour. Maybe I can, like, wear a mask. I don't know. That sounds creepy when I say it out loud. Definitely some intro music, though. Anyway, so let's wrap this up really quickly so you're not sitting here for a long time. Bonds you need to know. Covalent is going to be shared electrons equally. Normally, that is two of the same elements, and we'll talk about why. If we look at hydrogen, their nuclei are identical, essentially. Therefore, they have the same pull on the electrons that are being shared, and so those electrons get shared directly between the two, making it a covalent bond. So if we look at other elements, when we combine water and oxygen, when we combine stuff from methane, so carbon and hydrogen, the sharing is not equal anymore because the nuclei are different sizes, and so we get different types of bonds. The key to this is understanding electronegativity. And if you remember, electronegativity is the desire for that atom to pull electrons towards it. As you go from left to right, and you can see it on this diagram, as you go from left to right, electronegativity increases. Left to right, and then it basically goes diagonal upward. So if you look at the top, you can't see what I'm pointing at, but if you look at the top right portion where it's red, those are the most highly electronegative. As you can see, noble gases are not on that because they don't interact with anything. That those ones have 7 valence electrons, so their desire to pull another electron close is very strong. Whereas in the bottom left corner, they only have 1 valence electron, 2, and their nuclei are very small, so their desire to pull an electron close is very low. They're usually going to be the donors in an ionic or polar covalent situation. So, for example, when we have our polar covalent bonds, so we go from covalent, which is equally shared, to polar covalent, we see still sharing but unequal sharing. This is because there is a difference between electronegativities. In water, we see that oxygen has a stronger pull on the electrons because oxygen has a larger nuclei, and also because it wants to fill its shell, and hydrogen only requires 2, so it's not like fighting for these electrons, and so it pulls the hydrogens and the shared electrons slightly closer to the oxygen than to the hydrogen, which is why we get partial positive and partial negative charges. We call it a net dipole moment. Basically, it means that a dipole means that I have my molecule and one side is a little bit negative charged, one side is a little bit positive charged, similar to a magnet. Same thing. Ionic bonds, itchy back, help. So ionic bonds are going to be that the difference in electronegativity is so great that the larger atom literally rips an electron away from the weaker atom. Once that electron is moved, we have 2 different ions, and those charges cause them to be attracted. So a lot of the time people think, oh, the transfer of the electron is the bonding moment, but they rip the electron, a loss of an electron makes it a positive ion, the gain of the electron makes the other one a negative ion, and then they're attracted to each other, creating your ionic bond. Knowing these terms is also going to be important. You might want to pause it and take a look, but I think that we're hopefully familiar with these terms. So IMFs stands for intermolecular forces, which is going to be basically how electrons are shared. They are specifically, one example of this is London dispersion forces, because, and it essentially is, if we think about it, electrons, even if they're bonded, are still moving. And so that negative charge that the electrons have is not always in one place. Therefore, the concentration of negative charge or a partial negative charge is not always in the same place. They can kind of pile up in places and create a dipole. So when we look at the symmetrical distribution, the electrons are kind of all spread out evenly, so they are neutral, net charge of 0. Sometimes all of the electrons, because they're moving randomly, could all be on one side, and we get a negative, a partial negative, or a temporary dipole. And so that can happen. Again, this is all examples of, right, if we go down the row, when all the electrons are shifted over to the right, to the left, etc., they can cause partial charges that aren't always there. They'll disappear as the electrons move. Why is that important? Because for some types of elements, it's going to allow them to have certain properties, and hopefully we're thinking about water. In the water molecule, we have those dipoles, or partial positive and partial negative, and so those compounds interact with each other in a very specific way. Sometimes they can be induced, which is what these slides are talking about, which I doubt this will come up on the AP exam, but if you think about it, if I have an atom with equally distributed electrons and something with a partial positive comes along, all those electrons are going to kind of rush to the side that they're attracted to, creating what we call an induced dipole. Again, this is talking more about inducing a dipole. Basically, if one thing that has a dipole shows up, it's going to make the other ones create a dipole because those electrons are going to move towards what they're attracted to, which would be the opposite thing of themselves. The most important case for biology, obviously, all of that buildup is just to talk about the fact that because water molecules have partial positive and partial negative, they interact not only with the two hydrogens and the oxygen, but they interact with each other. Hydrogen bonds are an example of an intramolecular force due to the dipoles that are created in that polar covalent bond situation. So this gives them very special properties, and hopefully we remember all of this. This also means that if there are other molecules and compounds that also have dipoles, they are more likely to readily dissolve. This is why water is a great solvent. It dissolves other polar covalent substances, right? This example on the slide is ammonia. Also, because of hydrogen bonds or those intermolecular forces, we have higher melting points, higher boiling point, which is why water can retain heat so well. Surface tension, right? The ability to like move upwards in a plant is due to hydrogen bonds as well. All of these things are because of those dipole situations. The last thing that you need to just think back to is that we have molecular shapes. Hopefully we can determine, based on how a compound is set up, we can determine its three-dimensional shape. Right, we have linear, bent, trigonal, planar, tetrahedral, and I don't think that will ever come up specifically on the test, but knowing that could be important. If you don't remember, and we probably won't practice this too much, but if you don't remember how to set these things up, we can talk about it in class, how to go from the number of electrons and bonding to figuring out its shape. Because I did teach chemistry before this, so I mean, I'm not great at it by any means, but we can talk about it if we need to. The reason that this is important for biology is that things that have similar structures are going to have similar properties as well. Again, if we want to talk about how we create the Lewis dot structure and then how we determine molecular geometry from that, we can talk about it. We'll practice this a little bit in class. So why is this important, and what are we going to talk about later? Your DNA, everything is made up of these elements, and the way that they interact is based on chemical compounds, which is why we have to have a good understanding of chemistry to understand the natural world and to understand biology. This is an example of why we need chemistry. It's because we have AT and GC, right? They bond together to make that that ladder, right? That double helix. And if the adenine and thymine didn't bond, or guanine and cytosine didn't bond, and they weren't reactive, we wouldn't get that structure to form. Other things to think about, like when we think about the unit we just finished, is all of those hormones are just chemical compounds, and they need to be able to react with other things like receptors to make a change happen. And so this is also why we need chemistry as part of our understanding of biology. I showed in one of the classes, just looking at like how we can mimic naturally formed chemicals. Endorphins, right, you get when you are running, well, the runner's high, or you're happy, and morphine is just a slight change from that, but that can make it much more addictive. The same with it being a painkiller. This is why a lot of painkillers are highly addictive, because they are so similar to what we naturally form. So things that you also need to remember, energy must be added to a system to break a chemical bond. Energy is released when bonds are made. I think it's easy to think about energy being released when we break a bond, but it's the opposite. And so we just have to remember this concept as well. Other things, chemical reactions are the making and breaking of chemical bonds. It's as simple as that. We start with reactants, we finish with products. If you remember balancing equations, things like that. For example, reactants, we have the reaction, we make the products, hydrogen and oxygen making water. Again, thinking about reactions is super important because we have it in cellular respiration and photosynthesis, which we will talk about more. And then finally, understanding chemical equilibrium. We need to understand that we always have the same amount of stuff that we put in coming out. It just looks very different sometimes. And it always has to be in a constant ratio. There's very specific balances for that too. This is all review again, so hopefully you feel pretty confident with this stuff. So this ended up being a little bit longer than I intended it to, which is fine. At this point, you're going to pause the video. You're going to make sure you have all your questions written down and make sure you have a good understanding of this. In class, we're now going to take like a mini quiz and do questions. Normally you would watch these videos at home, and then we would do the questions and the quiz in class. But I want to give us one day to practice doing this and feel comfortable. So if you need to go back, please go back and watch more of this video, and we'll talk about this in class.